questions about the class project, the presentation, which makes sense because it is starting to come up. The general comment is, if in general people try to spend too much time and energy explaining why what they're interested in is important or useful. That's a very, very common thing. You only get 10 minutes or a few minutes with us to talk about your project. We know that anything you're interested in has some applications, and we're not as interested into that as we are into you taking a more engineering approach to look into that problem. So sometimes it may be like very detailed review of how things are processed, and that's perfectly fine. There's no real framework as long as it's you go back to the framework of the class. We're dealing with structural materials, and we hope we taught you a little bit how to process, how to think, how to select, and some of you may have done a project that relates to making use of a new design, a new material. And a lot of times there are lessons learned from that are engineering that you're welcome to use and talk about. There were a few examples. People are doing research thinking, oh, we're trying to optimize this structure so it deforms a lot without breaking. It's not an uncommon application. But he said to me, I don't really know if it's actually going to be used. So, some of the aspect that he was interested in when I was talking is, okay, so what would you use that for? So in buildings, you have situation for a seismic event that you really want the structure to absorb energy and not fall. So how do you do that? You don't do it through the welds or the bolted connections or the concrete. You do it through the structural steel. So you have to make your structure, and the example I gave, which is not uncommon. So you have main columns in a very large, skyscraper that you have to brace together. So let's say I put a brace between them. So what happens in a seismic event is it's not all going to lift at the same time because the earth, all the foundation goes through a wave of movement. So if this column tries to go up, this one's trying to go down, you can't just completely prevent it. What you can do is have this member in the center or in these zones deform permanently and absorb energy. So it's done for a very large building. It's done, of course, when you have high security system like a nuclear facility. All the frame needs to be very well designed so you will absorb energy. So you don't want any welded connection or even bolts in the areas that are going to be your shock absorbers. So we were talking about a dome. So let's think about the MIT dome. Just as an idea here, let's say we were in California and we worried that the dome is going to start to crack and deform if there's a seismic event. It wouldn't be unreasonable to think that may happen. So what do we try to do? We could say, look, if we start a new dome from scratch, this is a very big structure, we could say, here's my connection to the main building. I would rather not have a lot of deformation going on at that location, at that corner. So what if I make the dome thinner here, same principle, somewhere in the middle, so if it has to absorb some energy, and that could even be, differential thermal expansion from summer to winter. If you have a way that you can accommodate for it in the primary structure, then you'll win. So it's kind of talking about, it was a research project of stability and deformation and why you would want a membrane to buckle internally or deform internally, and I could see that as being one application. So what I say is, if you take something that you've already done, try to bring in to yourself first a new perspective on it. You know, try to learn something more, and then you can present that. A lot of times, if you went through a design and it hasn't been fully tested, that's fine. You know, it's not uncommon that you work on a project, you had some ideas, but you don't really know if it's going to work or not. So in those situations, I would say think about at least what is the envelope, what is the objective, and what are the pitfalls, the constraints, the things that you really could cause you problems. They're always there. You know, sometimes it could just be cost, but a lot of times you have other concerns. If you're trying to build something new, you need the people that are going to be use it to accept it, you know, to like it. It is an engineering consideration because, as you probably have learned several times from Professor Eager, in engineering, we don't do things just for the fun of it. We have a very specific application in mind. So to the extent that you keep in mind in your presentation what exactly is the ultimate goal, the usefulness, you'll do great. You can start from there and then work to what you need to convey to explain why you think that's important. So you're welcome to send emails, or we can meet after class or at another time. Next week, my schedule is fairly open right now. Just to make sure that you benefit from the exercise. That's the goal here. So for today, we'll finish on the factors of safety. And those dates here is just, so last class is on Tuesday. You got 3 days off. It's not a whole lot. And then we're starting the presentations. It's a condensed schedule. Professor Eager mentioned if there is, for some reason, somebody on the video cannot be here, we will accept that you video and send it to us. It's not the most interactive way to do things, and that probably doesn't apply to people here in the class, but it is the option as opposed to trying to continue on with the class past spring break. So it's going to be essentially a half semester class. The module summaries, there were questions on that as well, and I think we were clear from the beginning that we want you to relate what you've learned and make it an exercise useful to you. If you want to use bullets, if you're able to do a quarter page on a module, you know, it is what you want. We have a bigger class, so we won't maybe go as detailed in our review and feedback, but I will try to give feedback on those that submit for my module, even if there are many of those. So, okay, factors of safety. I brought a fracture surface, and maybe what we'll do is we'll stop a little bit short to the end, and I'll go through that so those that haven't done it already. And we'll kind of make a wrap-up of what we've been talking about in the past 7 or 8 lectures. So factors of safety, what we said on Tuesday is it varies a lot. So there will be some industries that will have a big number. We talked about pressure vessels. We said for the pressure vessels, it wasn't really an extra factor of safety. It was just the way people calculate loads. Yes?
So what's OSHA? I think the Office of like
Safety
Health
and Health Administration. Yep. They come into a lot of things. OSHA comes involved a lot in construction. They don't come involved in passenger car, for example. That's because that's not related to work. It's for service. So the OSHA regulation is one of the most stringent. It's one that has the actual safety factor much higher than in other industries, for good reasons. Some of the very, very large structures that, to some extent, when we're talking about the levee can't go anywhere, and there's only so much water it's going to be able to hold. So that's one idea why people will accept a smaller overall factor of safety when the loading conditions are very, very well established, and there's a whole range in between. So factor of 2 is typical, but let's say you're thinking about a building, but again, it's not a real factor of 2. If people do very, very detailed analysis, so if they go through a process that's similar to building an aircraft, then they do end up being able to use a lower factor of safety. So it's the factored load resistance design approach that has become more common for advanced constructions. You learn more, you specify more clearly what your materials are going to be, and you analyze in more details the maximum load that you'll have, and then you can end up with an actual factor of safety of only 1.25 as opposed to 2. We will talk now a little bit more about the statistical significance of the factor of safety. So and there's a good book, a very detailed book on statistics that I'm referring to here. It's not as practical as what I want you to get out of it in the limited time we have. So here we have the capacity of the material, and we have the overall demand that it's subjected to in this failure boundary. So you try to operate in these conditions where you don't have a failure, but you know there will be a certain combination of parameters that are going to make you fall beyond the failure boundary. It's almost inevitable that there will be a remote possibility, whether it's a 0.1% or 100%, there's always a risk, essentially, in most structures of a failure. So the way we think of it, and I do want you to think of this, is depending on what you're trying to accomplish. If you're trying to make a bridge over the city, like a highway over the city, it's very, very, very different than if you're on an offshore rig that has all these safety procedure and alarm, and everybody can just exit the structure if something goes wrong. So there is built into decisions about safety that are a function of the number of people that would be affected by a failure. It's not necessarily an engineering decision, right? The same way that when we're thinking here in the Boston area, we have all these aging infrastructures. It's not engineers in general that make the ultimate decision, we're going to replace Longfellow Bridge next year. It is the public. Somebody has to fund that. It is based on a lot of recommendations made by different people and, risk of failure. But the bottom line is the more consequential the failure is, like a nuclear power plant, the more we want to be conservative in our factor of safety. And that's built into these probability equations where when you start taking into account the number of people, your factors of safety is changing. And it doesn't have to do with the detail, how you make the design. It has to do when you compare your worst case load with your lowest capacity over time. Because that's, when we talk about statistics, if we think about bridges, they will deteriorate. I worked on the collapse of the I-35 bridge in Minneapolis. That was a while ago now, I guess, 6 years ago. It happened in the hottest day of the summer, August 1st, 2007. What happened there is not fully understood, of course, because there was only one security camera that actually captured a little bit of what was going on, but it wasn't even centered in the area where the damage started. So you have a lot of mangled steel at the bottom, and you can try to do your best to analyze it. One of the features of that bridge that's relevant to us is it was called a fracture critical bridge because it only had two main truss to carry the load. And you see that on the photograph. So you have one truss on one side, you have another on the other side, and everything else just diagonals. So if one truss fails, everything comes down. It was very common back then. Nowadays, you try to have more redundancy. So what happens to these trusses? They are very, very long. So you go from one side of the bridge to the other, and I won't draw the truss structure, but let's say we have multiple spans, and then we try to cross, and this is all steel. So from seasonal variation, it will try to expand and contract as opposed to the shores. And the way to accommodate this is expansion joints. So over here, if you go to the foundation, you have a roller system that's going to allow for the bridge to expand. And this one, let's say it's going to be fixed. It's fairly well established. So NTSB, National Safety and Transportation Board, got involved to analyze this failure because it was very consequential. It wasn't at peak traffic hours, but a bridge at traffic hours, you just don't want it to fall. So what they were able to observe, and it wasn't maybe emphasized as much as I wish it did, is there was packed rust into this expansion joint. So the roller system to allow this entire section to move back and forth was not working. Now, I don't have the distance exactly right here. This is really, really wide, and it has this arch structure. So if this gets fixed in a cold day, what happens after that is it's going to bow and build in a lot of compression when you heat it up. So as you go through the summer and you really, really are compressed, one thing that I believe happened is eventually you overcame the rust on this bearing. Now it starts to let go and releases dynamically. Now, can we think of the designer of a bridge doesn't assume that you're going to have a factor of 2 of live load with respect to the entire weight of the bridge and all that. It just isn't part of the equation. So when I try to explain why, despite our best effort as engineers, over time, so this is when we talk about lower probability, it means it's great at the beginning. Over time, your factor of safety is going down. Is it because you have more events going on? That's one option. Your conditions are changing. So back in the 50s or 60s, they didn't necessarily have the kind of salts that we use nowadays to make sure there's no ice on the bridge. So conditions have changed over the years, and the capacity has changed because of, I guess, not a complete maintenance, right? If in an ideal situation, you look at those bearings all the time and you make sure that they're moving. It's not unreasonable, I think, to just say, keep track of the movement from season to the other, because you'll have people on site to look at these things all the time. So it's being inspected. But the question is, what are they looking for? Well, they're looking for things that have been a problem in the past, not necessarily everything that could potentially go wrong. And that's where things just become very, very difficult, even with experience. And now what they do with these old bridges, there were other issues, of course. There was some issues about the thickness of some of the materials to make the joints. There was some corrosion of those members as well. But that's really where I say that as opposed to building something and doing a proof load test or doing a test run, when time gets involved, your risk of failure always goes up. So it does come into my practice right now with pipelines. So pipelines, if they're in the ground in average for 30 or 40 years, of course they had some corrosion. Of course, they've been through some cycle of loading, and there's going to be some fatigue cracks in them. And therefore, the way people used to think of them for design and strength purposes when they were new don't apply anymore. So the same way for an old bridge like this, okay, well, was it built to code back then? And in that case, no. So that's already a problem. Was these, if let's say this, was these calculation the code take into account everything that has changed since then? The answer is no. They added lanes and they added, de-icing systems that were just a lot more aggressive to the steel than the old stuff. They had runoff of water to feed into the expansion capability, the sliding capability. So no there, and then anything else that has changed, well, the steel is still the same. So that's good news. If you want to blame the steel in this case, I don't think it would be fair. There's just a lot of other things that became a problem over time. So what we try to do, if you're building something, I think you have to identify in which category you fall. Is this a new bicycle for a race that the guy is going to be ready to fall to the ground and be safe anyway? That's a good situation to be designing. So you can say at the very extreme limit, yeah, the whole thing is going to fail as long as it doesn't create an injury. You may be okay, and that's a problem with composites actually, because they fail in a brittle manner. People can get injured, so you want to work on how it's going to fail so it's not consequential. I hope you gather that a lot of it is from experience. You have to think about all these extra parameters, temperature variation, rusting, that will ultimately happen. Maybe for you it's environmental degradation. If you have these expansion membranes, just cycling. If it's a stationary structure, but it does go to temperature variation, it will be essentially subjected to cyclic loads every season. Moisture can really be a problem. So I talked about statistics just for two main purposes, is to make you realize that if it works for a year, it doesn't mean it works for 10 years. It works for 10 years, maybe not 40 or 50 years. So it takes a long time to build that history. And it is, I guess, a legitimate reason why a lot of times you don't want to start from nothing. You don't want to be, oh, I have this great idea. I'm going to create a completely new kind of bridge. You can do that and then go back to everything that has been learned in making bridges in general and apply those extra parameters, extra constraints to your situation, but it's a lot of work, so that's why for critical components, incremental improvement is a lot easier than a complete breakthrough. Not that you can't do it. Like we are now using composites, we covered that in class, in airframes, but it took 20 years from the time that it was completely feasible to the point of actual implementation for commercial use. So it's unfortunate, but at the same time, it's for a reason. It is for safety. So this piece is heavy. We're going to switch gear. I want to talk with you about fracture, for the reason that in the context of trying to learn from history, when something goes wrong with a prototype, which is happening to us right now a lot, you can learn by going back and through the details of what happened. So the one example I brought to class, and I circulated at the front, so I'll do the back here. Can you come closer? So what happens to this one is just a big shaft that's under bending load, and it cracked very, very slowly. So the crack started on the surface, on the outside where the stresses are higher, and it gradually came to the inside. And you see all these lines, just like tree lines, that tells you at each point in time I was at a certain penetration into the section. And the area of metal left before the final fracture is just a small little zone here in the center. And you cannot believe how many times I've seen this situation where somebody brings a broken piece, say, oh, it wasn't strong enough. A lot of times that's not true. It's not a question of strength. It's a question of resistance to crack initiation that was the problem. So in other words, it's not that the load was so high, it's the load was a cyclic load. So what you do with bolts, for example, you eliminate the cyclic load. And there are ways to do that. In the case of this shaft, I think we were saying it was relatively easy to initiate cracks because we didn't have just one. We had one on this side, we had one starting from here, and we had another one there, and you can see the step of where they try to merge. So by knowing that it was 3 cracks, we can eliminate the idea that it had only one defect in the entire sections. There were at least 3 defects. Now, it's not as much if you remember when I brought the plastic pipe that had 100 sites. So when we have 100 sites, we know it almost started to crack right away. Here with 3, there were some weaknesses. So that in this area, probably the coating was not as performant. Bless you. Maybe there was a notch in the surface, but essentially something happened at those 3 locations to make the crack to initiate. And it took time for those cracks to initiate, because if it happened the very first day this axle was used, you'll have crack all around it, and we don't. So this is an intermediate situation where, see, there was deficiencies at the initiation sites. We can't analyze them very much. This is being worn out after the fact. That's why you have the lip here. And there was a question earlier about the lip. So in this case, you don't really have a lip. You have a zone of final fracture. It's just very, very small, which means the day it failed, there wasn't anything special with the loading. It was a normal load, but it's just the entire history that caused this to happen. Good question. So you have to know the load applied and the capacity. So if you have cyclic loads, there are materials that are more resistant to that crack initiation, and that's what you're looking for. The other thing that you can look for, if in the context of landing gears, for example, is you just assume there'll be a crack to begin with, and you don't want that crack to grow big enough to cause a problem. Now, on an axle or anything that is really vibration load, it's almost impossible because you start getting millions and millions of cycles very, very quickly. So if you expect millions and millions and millions of cycles, 100 million, you don't want a crack to start. If you only have up to 200,000 cycles, you can have a design where you say, you know what, it's not great to begin with, but I don't want that crack to grow beyond a certain limit before the service life.
Are known for being crack resistant or propagation resistant?
Okay,
No.
yes, it's a good question. So about the crack propagation resistance of material, there's no magic solution. In general, when you increase your yield strength, you do increase your resistance to crack initiation. And the reason is, and that speaks slightly different topic. We're talking about fatigue, but it's perfectly fine. So let's say I have a piece of material, and for now we'll say it's a piece of metal. The good thing with metal is, yes, with metals there will be a certain value of the cyclic load. So in this case now we're going and loading and unloading and loading and unloading. What happens is if this stress is significantly less than, let's say, half the yield strength, the way I'd like you to think of it is locally into this material, there will be inclusions, there'll be some anomalies, and around the anomaly, you do have a stress concentration. You have extra loads that are not part of your nominal load. So if you're above a certain threshold, even though the entire member is elastic, just like a spring, locally you start having this real plasticity, like a permanent local deformation, and that what will create the initiation of the crack. So on a metal, you can set a criteria, especially steel. There will be a certain value below which you're okay. You will not initiate crack. Now, essentially for crack initiation, you want this to be high. And that's why we do surface treatments a lot. And that axle did have a surface treatment that just didn't work. But that was the idea, to raise the surface yield strength so you don't have that crack initiating. The real downside of doing this is a lot of times your fracture toughness, so your resistance to a crack, is going down. And there is no perfect solution. Yes? To an existing crack. So when you raise this, so as your yield strength is going up, generally for a certain category of alloy, your fracture toughness is going down. So in the case of our axle that we looked at together, it was structural steel, well, probably a relatively high-strength steel. But the idea with it was to try to be a compromise. Because if you go too far, you take a ceramic, just at the extreme, your fracture toughness is extremely low, and you lose overall. So it is a compromise between crack initiation and then the resistance of something that is crack to an overload failure. And I'll show you an example here that is slightly different. Yes?
Quick question. Are there any equations that can predict how long it takes from the time a crack initiates to the time the crack?
Yes. So I will refer you to the life assessment module that I listed. It's 4 to 6 hours, very specifically on that, on how to deal with existing cracks. Yes. So what happens here is you start at this very corner, and there's only one initiation site. This is another shaft, and you can still see these beach marks showing where the crack was at a certain point in time, and it grew all the way to about 40% across the section. And then it failed. So another situation, in this case, we have one initiation site. So definitely something was wrong over here, because otherwise we'll have many initiation areas. So it's one initiation, and you see the crack propagation lines. They're a little bit like sun rays. They radiate from where the crack started. And over here, there was a little notch. There was a surface damage, which is very, very common. So when you have something that fails over time, especially plastics, are very notorious. If you have just even a scratch on the surface, if the loads are significant, that's where the crack is going to start. So the crack starts, and it goes through a certain growth rate, and there are equations to predict that almost exactly, and then it fails. Now, once it's failed, what can you do? Well, you know that you did have a certain load, but the load was nowhere near the yield strength, because you cracked 40% through your section. So you know that the load, especially in bending, was probably only 25%. And I'm guess this is estimated, but it will be of the order of 25% of what it will take for that axle to actually bend permanently. So, not excessive load in the term of short-term use. So instead of being here with this half of yield strength for crack initiation, we know we were 1/4. So what happens? 1/4 is because we had a notch on the surface. So in addition to having some local, so our situation with this shaft is, it was like this. You had a little notch. So you get your KT here. Maybe it's 2, and then you get an extra stress concentration at the little particle in that notch, and now it's only 25%. So it's how I want you to start thinking when you have cyclic loads, or if you have sustained load with plastics, your capacity is always going down significantly. We're not talking 20%. It's factor of 2, factor of 4, factor of 10 sometimes with plastics between the short-term burst resistance and the long-term capacity. Was going fast here. We'll go through another example here of a failure and how you can learn from the fracture surfaces. It's a diesel engine, combustion engine, and you have the intake and the exhaust valve that just open up and close. So it's relatively, these valve systems are relatively simple. Let's take some space here. So I have the inside of the engine right here. And we have a valve that wants to seat in here. We'll make it very simple. And that's connected to a rocker system that will lift it, and you have some spring. So you try to open this and let the gas go exactly in the cycle where you want it to go. There is very, very little force between the head of the valve and because it's only a spring, and the only thing you want to do is not have a whole lot of flow of gas when it's in closed position. So what happened is it failed right here at the junction, which means when it was coming down to close and you had the combustion pressure, there was a little too much force over time. And we are talking very, very large number of cycles. So they made these engines for a long period of time. What happened? You go and you look at that fracture surface, and it's a very, I'm sorry about, it looks great here. It will look great. The notes are already online, but it's a similar situation where this was a slow crack that went all the way to here, and you just had this little moon shape at the top at the final fracture. So what does that tell us? Because it's only supposed to be held in tension this way. We know it started essentially from one side and went to the other. So the valve was not sitting perfectly square on its seat. There was a little bit more load on one side than the other. There were just documentation here. When you do these things, you have to, before you clean it up, to look at it more carefully, you have to document the conditions. So if somebody else wants to review what you've done, they can do that. So once it's more clean, you can see more clearly those two initiation sites. So it's the same effect where you have the crescent shape, the beach mark. There's a crack until this point, so it gives you an idea of where the initiation was. There's another one here that may look a little more subtle to you, but there is another region that goes all the way to here, where it also grew. Eventually, those two cracks merged to make the main crack. Oh, here we do see. This is the overload line where we reached our fracture toughness value. So a lot of life spent, again, in growing a crack. And the question which you guys brought earlier, okay, so why did the crack start and how could I prevent it? So if we want to know that, we have to look close to the initiation site. In this case, it's hard to know something. I mean, maybe here there was a little bit of a missing material. That's what it looks like. But it's not super conclusive, at least on first view. On this one, oh, there really was a hole. And that's why you see you don't have the focus in this area. So this is a cavity that has a depth to it. And what is very, very interesting here is you see a lot of lines starting from the edge of that cavity. Does that tell us anything? Yes, it does. So what it tells us is you had this corrosion pit, which is big. This is about almost 0.5 millimeter. It's visible. That happened first, and then you had these cracks starting from it. So I bring this one up because it's a simple way, and you can see it once these parts were clean. Yeah, they had pit on the surface. So the things, when you involve marine work, essentially the whole vessel sank. Okay, so of course it's corroded after the fact. But one of the questions was it corroded before or after the failure? Okay, so essentially the fracture surfaces are giving us that information right here very, very, very clearly that you had a hole and then you started some cracks after the hole was formed because you have all these small initiation sites around the hole. If this crack started here, it wouldn't be giving me all these initiation sites. It wouldn't give me a 20 initiation sites all around it. So it's a way after the fact to say, well, because there was a maintenance history on this, so essentially at some point the water got into the engine, it had some corrosion, they didn't clean it up completely, so the fatigue started and then they had the second incident, as opposed to any other way around where it just failed by the loading and then caused the problem. So maybe one thing that you'll really remember is the surfaces are really important in terms of the resistance to cracking. The surface treatments for that are more in terms of steel. So with steel you can create a lot of surface treatment, like carburizing will bring you a lot more yield strength on the surface. You take the part and you heat it up in the oven, you put it in on the carbon atmosphere, and the carbon penetrates, you cool it off, and now you have a very hard surface on the outside, and you have a strong core. So what's the advantage of that is you work, just like this axle, that was the intent. You work to increase your resistance to crack initiation on the surfaces where the cracks will grow, and then you want a soft core that will resist better the existence of cracks. It's used with fasteners a lot and different high strength application, the surface treatments. And that's something that we cover in the fall, and exactly how you do that.
Question on that.
Yes?
Surface finish, surface treatment. Is surface finish a property that really matters? I mean, I know when you pass something, it's rough finish.
Yes.
A machine part, for example, before you treat it.
Okay, so the question was about the effect of the surface finish. It will be important if you're doing a lab experiment. If you're trying to determine the strength property of the material itself and you have a clean piece, it will matter a lot. For a practical application, a lot of times there you have something additional than just the surface roughness that's affecting the crack initiation. Whether it was a little bit of a wear line, or whether you have a large inclusions, whether you have a weld that is just a pure stress riser, the toe of the weld. So a lot of times it doesn't matter. It will matter if you have a very detailed machine part, and maybe I'll insert it in a slightly different way. Let's say you have a shaft that needs a little reducer in it, so you're looking at something like this. The roughness in the sense of how smooth this radius here is very, very, very critical. And I've seen it too many times that people will put a design together and actually don't specify exactly what they want in these corners. So you can't imagine how many times I've seen it. So in that sense, exactly your radius, your minimum radius and the tolerance of it in this area is extremely important. If you have a relatively big part, like I think I showed the example of a fitting, the outside surface of the fitting in general just doesn't matter at all. What is going on at the root of a thread for that fitting is really where the stresses are. So if you have, for example, with a threaded connection, if there is any reentrant corner, so if it's machined sharp like this, or if forging caused a little bit of a notch here, which happens, then that's where your cyclic resistance is going down. But it's not by specifying just the overall roughness of the part in general that you'll gain a lot. If it's a great shaft that sees no wear, That is one example. Let's say this is loaded and bending, and there's no discontinuity. This is a very smooth surface. Yes, you may be able to raise, maybe you'll raise it 20, 30% by having a very nice finish here. But a lot of times there will be something else. There'll be a wear line that you do have to take into account, and it's going to. It's yes. So you can, if you know there won't be any subsequent damage, to rely on a greater finish, but it's a minority of general applications. It was a great question. Any other questions? So I'm sure you're not stressed, so we won't spend a whole lot of time doing a recap. The good thing is it was over a three-week period, I think, from the beginning to the end, so hopefully you'll remember something. We started talking about performance index, and one thing I tried to do there, because I knew Professor Eager was going to emphasize steel, is we talked a bit about plastics and we talked a bit about composites for aircrafts. So it's because they're more expensive, but when the performance is what you're looking for, you are willing to pay more per pound. Is that simple equation that I'm sure he explained in great details. We talked about the material and process specification, and over there it really was, are you asking for a chemistry? Are you asking for a certain property? Or are you asking for good control over everything? You know, how it's joined, how it's inspected. Those were the high points there. On our last lecture, we started talking about factor of safety, and the one thing that I really wanted to emphasize there, instead of saying, well, experience helps, I hope that with the example of the bridge and looking at fracture surfaces, you're starting to see why it may take 10 years to develop a new code for a certain application, because it just takes time to really know what are all the parameters that are going to matter for a certain application. Now, all these codes are not perfect. We talked about the pressure vessel. It has a very, very specific way to deal with how to calculate a factor of safety that's very, very different than the building, very, very different than when you build an aircraft, very, very different than if you do a car. The car, it's overall performance. So you don't have to go as much to the drawing board to justify your design. So it's a very, very different industry with that respect. Failure analysis, I was hoping to do a little bit more, but it was a condensed a module, and I hope that by bringing one case here and there, when we did the World Trade Center at the very first lecture, I said, this is how we improve the code by knowing exactly how it failed. Going over any fracture surface, well, it corroded. So if somebody wants to start saying, well, maybe we need to redesign this valve. No, valve's fine. You just lost a factor of 2 or 3 on your minimum load. This equation here that will start causing fatigue because you had corrosion. So, so that's not an issue with the design at all, and you just move on. You say, this one piece of information is not a good reason to go back and make the valve stronger. If something else happens, then of course you need to keep your eyes open for that. So the 4 extra hours for the modules, I'm not going to be asking you specifically. I think it'd be great if you pick one and you have something that you've learned and you want to talk about it. And you have a lot of options. So the life assessment is where we specifically talk about fatigue, how to design to prevent crack initiation, how to design to prevent crack propagation. Environmental and mechanical behavior, I talk about brittleness, which we couldn't cover in the time we had. Welding and corrosion, that's the 3rd bullet over here. And then if you're more interested to learn about other aspects, other materials that we just didn't have a whole lot of time for, that's a slightly older version of the class that's different. And if you have anything in particular, I can point you. I kind of know where everything is. And so I'm not expecting you to be at that level. It's, you know, there's a lot of history over the past 5 years of changing things around. So you're welcome to shoot me an email. And I think you have that. It's on the Stellar. But so just CMO, CB, MIT. I did want to say something because we try to show you some practical aspect of engineering, and then the question is, what are you going to do with it? So some of you will end up doing research and may benefit from the class just in thinking, well, you know what exactly are we trying to achieve here? Ultimately, would this be used for? That's what I did with my thesis. A lot of people in my group were working on indentation work. And I said, you know, I'm interested in mechanical property. I do think that frictional sliding, so movement of surface with respect to each other, may be more relevant to a practical application. So I just went on and started doing these things. And you know, my path to be here today to start talking to you about engineering, it's just really been moving from research to consulting, and I've been very, very active with a startup company with developing new technologies. But it's very, very specific to me in the sense that I would say I valued it the most. I want to be accurate, and that's is one thing. It's not that I want to be doing everything. I want to do the things that I'm doing in a very, very clear and clean way. And I do also have entrepreneurship interests that I carried through from moving from a big company to having my own consulting and now having a startup. But it's all personal, and I think I want you, a lot of you are senior, this is probably a time to look at a job. Think about what you do best. And it's all different for every one of you. So that doesn't have to be in your summary notes, but you know, essentially some people will be just very, very curious. I'm not. So if you ask me questions on things that I never needed to know, I may not know them because my interest normally is in terms of what I'm going to be able to use. But so I'm not the best person to do you know, science research to publish in Nature, thinking like maybe in 20 years we'll find a use for this. That's just not me. But there will, I'm sure, be here or in the institutes we have a lot of those people that are more long-term researchers. And there's a whole range in between. So I'll leave that to you. And thank you very much. It was great.